let's look at definition of a plane in 3D. So I wrote a few things down here first, so copy all this down. Definition of a plane. It has to be in 3 dimensions, otherwise it's just like the XY plane. So, so yeah, three variables x, y, z. We're going to define a couple things here as we go. So first, let's suppose P is a fixed point in space, P of x, 1, y1, z1. And then we're going to eventually here suppose that Q is points that vary. So Q is going to make up all the points in the plane. So Q varies. Q is arbitrary that satisfies the conditions. Okay, so it's the set of all points kind of concept. So write all that down. Q of x, y, z varies or represents all the points of a plane. All right, so here's the definition. So there are a couple ways to define a plane, or how you would determine a unique plane exists. One of them is basically 3 points. So if you have 2 points, then there's an infinite number of planes that go through those points, right? It could be that one or whichever. So you need another point. So once you have 3 points in space, then that would define a unique plane. There's one and only one plane that goes through those 3 points. Okay, so that's one way. The other way is basically this definition, and that is if you have this plane like this, then we want to consider all these vectors in this plane like that. Let me redraw that a little better. So all these vectors in this plane, where that tip is your Q, that varies, that is perpendicular to this vector n, which is called the normal vector. So we're going to fix a point. Q is the set of all points such that PQ is perpendicular to n, your normal vector. So as n changes, you're going to get a whole different set of Q, which are the points x, y, z that vary. So it's kind of hard to show you without actually having a visual. So take a look at the book, or we can talk about it more on Zoom or something. So here's the definition. So a plane is the set of all points Q of x, y, z for which the vector PQ is orthogonal meaning dot product 0 to n. N cannot be 0, of course. 0 vector. So this is next basically the derivation of the formula, which you would have seen before actually. So let n, maybe not quite in this form, but you basically have seen it. Let n equal the vector ABC in component form such that n dot PQ is equal to 0. That's what we mean by orthogonal, right? So then we have where'd it go? So then we have PQ equal to, so this we would have had this x minus x1, y minus y1, and z minus z1. Okay, because that's my PQ, because Q is the point that varies and P is the point that's fixed. So that's how we would write that. All right. So then what if you now what we want to do is do that calculation and we get our formula. So what we have then is N dot PQ is equal to A plus ABC dot that vector, x minus x1, y minus y1, z minus z1. And when you get that dot product, you can see, oh, and that's equal to 0. Well, you know what, I'll just write it like this. We'll just expand it and then say equals 0. Or we could do if and only if, either way. So you get A times x minus x1 plus B times y minus y1 plus C times z minus z1. And so that's equal to 0. So this form right here, we can call our standard form. Like that. Let's move it up a little bit. So that's our standard form. Or you can expand it out, either way. So that's equivalent to the slope-intercept form, the y minus y1 equal to m times x minus x1, right? Because you have a fixed point, you have the point that varies, and then the m is your slope. Well, A, B, C is basically like our slope, but it's not a slope. It's the normal vector of the plane. So you can expand that out into this form, and I'm not going to show all the steps, but if you expand it, then we have AX plus BY plus CZ equal to D, and D is just that expanded form. So where D is equal to the constant AX1 plus BY1 plus CZ1, right? And so either way is fine. Basically, they're used for two different purposes. The form of a plane that you would have seen before would have looked like this. You would have had basically AX plus BY equal, oops, that was a line, plus CZ equal to 0. So if you did college algebra or anything talking about a plane in 3-space, that's what it would have looked like. And that's essentially what we have. Not equal to 0, equal to a constant. Equal to D, like that. So that's what you would have seen. So it's really the same form, and now we used to use ABC. It's just slightly different. So the one I highlighted is really used for finding the equation of a plane, and the one that's I wrote down below, and I'm going to highlight now in orange. This one is basically what you would leave it in. Okay, so either way is fine. I know all of you can expand it out and simplify. So, okay, so that's what you need to know. The coefficient is the normal vector to the plane, right? So it's perpendicular to every vector in the plane. And then you're one of the XYZ is what varies, and then the other points, you have to have a point in the plane. So all of these are rely on having a particular point that you kind of pivot around, either the line or the plane itself. All right, let's look at an example. That's pretty much it, and then we just do a bunch of examples. We'll hit them here in problem sessions. So find an equation of the plane and here's your point, through the point 5, negative 2, 4, parallel to the plane 3x plus y minus 6z plus 8 equals 0. And that's the only question here. So you want a plane that is through that point parallel to the other plane. So basically what you want then is these planes like this. I'm going to draw a plane here. So you want this plane, maybe what's given, and then you want a parallel plane. So you have this plane here, then you want a parallel plane. So parallel plane would be like this. Okay, it would be this guy. So this is not written very well. Let me try it again. Actually, you know what the best way to do it with this thing is? Just copy it and paste it. So you have a parallel plane like that. Okay, and so what I'll do here, watch this. I'll erase some of it, and then it'll kind of merge up good in there. So if I erase this like that, then we copy it again. It's like that. Okay, so that's my parallel plane, and then I'll just kind of go like this. Oh, this is more trouble than it's worth sometimes. So the question is, what about the normal vector? So that's really the question. So each of these, they have a normal vector you're going to use, right? So this has a normal vector, and you can read it off directly from the equation. So if this is plane 1 and then plane 2 is below, what vector can you use? Okay, so this one needs a normal vector as well. So what normal vector are we going to use for those two different planes if they're parallel? So basically, hopefully you saw that. Parallel planes, you can use the same normal vector. Okay, so that's really the idea there. So use the same normal vector for parallel planes. Just like parallel lines, you use the same direction vector. Parallel planes, you use the same normal vector. So what is our given normal vector in? And you just read it off. 3, 1, negative 6. So that is 3, 1, negative 6, our normal vector. And then you substitute into this formula. Okay, so you're given a point, and we read off the normal vector, and then you just substitute in. Okay, so I'll write this up. So you have your formula for the plane a times x minus x1 plus b times y minus y1 plus c times z minus z1 equal to 0. All right, so then substitute in, maybe go ahead and finish this, and you got it. So 3x minus, be really careful. One of the common mistakes I see one or two students have is placing the point in for the vector and the vector in for the point. That's and obviously just an oversight mistake, but still it happens every time, and be careful. Don't do that. So make sure you're putting the vector in for the vector and the point in for the point. Okay, and so it's plus b, which is 1, and then then we have y minus negative 2, so it's plus 2. Plus c is the negative 6. And then z minus z1, so with the point that's given. And sometimes I like to go up here and say this is x1, y1, z1, so that I know kind of what I'm looking at. So z1 is your 4 equal to 0. So at that point, that's fine. I mean, you don't have to expand it. So expand if you like, or to check the book. Like if the book answers expanded out, then you gotta expand it out. That's something in a college, like an algebra class, I'd be like, yeah, you gotta expand it out, get it in a certain form, but not really here. It doesn't matter. So that's the equation of the plane parallel. Okay, so let's see. What do I have left? I have left another example. We're going to do a classic one where basically you're given 3 points, determine the equation of the plane, right? Determined by the 3 points. So that's a classic one I want you to do. We'll talk about sketching planes briefly, and then a couple more examples. And that'll be it. We'll do that in another video.